SpaceX just got approval for 2 Starship pads at SLC-37. That's 5 total pads capable of 152 landings per year from one site alone. Has any rocket ever operated at this scale? Meanwhile, B-19 defied predictions after the B-18 explosion, stacking sections at record speed for a January 5 3 debut with untested Raptor 3 engines. Can they pull off this high-risk first flight? And China's Methane rocket just failed. What went wrong? Let's start with what's happening at Starbase, because this pace defies every prediction. December 2nd, a 5 to A4 section rolls into Mega Bay 1. December 4th, a 6 to A4 section follows, forming the liquid oxygen tank body. December 6th, the massive fuel transfer tube arrives. December 10th, liquid oxygen header tank moves into position, 4 major booster sections in 5 days, and SpaceX hasn't slowed down since. If this continues, B-19 could be fully stacked within 2 weeks. After the B-18 explosion tore through tanks during a pressure test, analysts predicted months of delays. Instead, we're watching the fastest super-heavy production run ever. What changed? That fuel transfer tube tells the story. It's substantially larger than previous versions, nearly matching Falcon 9's scale. This isn't just bigger. It's a fundamental V3 redesign supporting Raptor 3's increased power while enabling faster flip maneuvers and potentially simultaneous engine ignition. But here's the key. SpaceX had to redesign the entire assembly sequence because this tube is too large to install late in the stack. They're building the booster around it now. That level of manufacturing adaptation while maintaining this speed signals SpaceX has moved beyond experimental development into production-scale operations. And the tube survived B-18's failure, relatively intact while tanks around it failed. That real-world stress test gave engineers confidence in V3's core design while revealing exactly where reinforcements are needed. Every failure becomes data accelerating the next iteration. Pad 2 is coming alive with equal intensity. 3 full-scale deluge tests in 1 week, December 5th, 9th, and 10th. From distant cameras, it looks impressive. From close angles facing the flame trench, the raw power becomes undeniable. Water explodes from nozzles with such force that spray reaches heights comparable to the launch tower itself. This isn't designed for current Starship configurations. It's built for what's coming, vehicles with thrust levels that will make today's launches look modest. S-39 reinforces this momentum, stacking complete heat shield fully tiled using the crunch wrap technique. This isn't experimental configuration with intentionally removed tiles. This is operational standard. S-39 could roll to Massey test site next week for cryogenic testing, followed by static fires in early January. Here's why that matters. Booster and ship test at separate facilities, so both vehicles advance in parallel toward a January launch window. Now, Florida changes everything. SLC-37 approval isn't just another pad, it's 2 complete Starship facilities at Cape Canaveral Space Force Station. The agencies involved weren't just NASA. Department of the Air Force, Space Launch Delta 45, U.S. Fish and Wildlife Service all signed off. That combination reveals what this represents. Military infrastructure for national security launches. The numbers are staggering. 76 Starship launches per year from SLC-37 alone means 152 landings since both stages return. Add LC-39A's 44 annual launches plus Starbase's 25 or more, and you're looking at 145-plus flights yearly across all sites. Falcon 9, the most launched rocket ever, hit 150 total flights in 2024 across 3 pads. Starship is designed to exceed that with 1 pad complex. Is this achievable or overreach? My analysis. The infrastructure demands are brutal, but the logic is sound. Orbital refueling requires dozens of tanker flights in rapid succession. Mars transfer windows demand ship fleets launching within days. You need distributed capacity with geographic redundancy. Florida provides access to polar and equatorial orbits, proximity to government customers, weather patterns different from Texas. This isn't aspirational, it's operational necessity for committed missions. But building two complete pads simultaneously creates unprecedented challenges. Foundation pits, tower segments, Mechazilla arms, flame trenches, orbital launch mounts, quick disconnect systems, everything doubles. Timeline extends to mid-2027, but that's aggressive considering scope. Competitors will fight this. ULA and Blue Origin here 76 flights per year and see airspace congestion, range conflicts, market domination. Expect regulatory pressure for launch limits and scheduling constraints. SpaceX needs strong relationships with Space Force, NASA, and FAA to protect operational flexibility. Political battles might prove harder than technical ones. Then there's production. Florida needs local manufacturing for sustained operations. The first gigabay started, but complete ecosystems take over a year to build. If lunar and Mars missions begin around 2027, construction must accelerate dramatically. Without local production, Florida's pads become expensive monuments. Fuel supply is equally critical. Liquid methane and oxygen for 76 annual launches require massive transport networks or on-site production. Storage, cooling, delivery infrastructure must scale proportionally. Flight 12 presents challenges more severe than most realize. Procedures might match V2 flights, but the vehicle is fundamentally different. B-18's violent pressure test failure proved V3's structural stability remains unproven under real mission loads. Zero flight heritage exists for many systems: new tank configurations, redesigned fuel routing, structural reinforcements all remain unvalidated in actual launch conditions. Raptor 3 adds complexity. Thrust increases to 280 tons sea level, 306 tons vacuum. More power means harder vehicle control, altered propellant consumption, increased structural loads, greater ground system impacts. The simplified design improves reliability, but creates inspection challenges. Welded structures replace detachable flanges. If engineers suspect problems, they must cut into the engine, effectively destroying it for flight. Stakes are high for static fire testing. The redesigned hot staging system represents the biggest unknown. Inspired by Soviet N1 but significantly modified, it mounts directly onto the booster, lighter and simpler without requiring jettison. Extended structure improves heat dissipation and pressure venting, but structural loads during separation, thermal environments, aerodynamic forces, all theoretical until Flight 12. The larger venting area directs more exhaust toward grid fins, increasing thermal stress. Any damage affects descent control and landing precision. Grid fins change dramatically. 3 instead of 4 creates asymmetry. One booster side lacks a fin. SpaceX claims no navigation compromise, but physics are undeniable. Asymmetric aerodynamic forces create control challenges. New fins integrate catching points into structure, demanding greater durability since minor damage could prevent future safe catching. On ship, the heat shield faces its ultimate test. S-39 appears fully tiled, but durability under extreme re-entry heating remains unproven. The shield must survive largely intact for rapid reuse. Extensive rework after every flight destroys operational efficiency. Aft flaps endure intense heating due to exposed positioning and broad surface area. Damage tolerable during experimental flights is no longer acceptable. Even ground infrastructure faces first real test. New orbital launch mount with upgraded flame trench designed for repeated launches, but this configuration never supported actual launch with history's most powerful vehicle. Miscalculation could damage pad, delay missions, affect safety. China's ZQ-3 failure reveals reusability's difficulty. Successful launch, clean separation, deployed grid fins, stable boost back burn. Then landing burn ignition triggered immediate catastrophic failure. New footage shows the sequence: proper grid fins, stable descent, landing burn. Engine bay erupts in flames, spreading rapidly as booster freefalls and explodes. Likely cause: leak during re-entry. Engine plumbing subjected to extreme thermal cycling may have cracked. Super cold methane or oxygen escaping near hot surfaces ignites instantly. Flash fire spreads through engine compartment, consuming insulation and structure while generating thick black smoke. But here's what's interesting. Crash site positioned very close to intended landing zone. Even with complete control loss, guidance successfully positioned the booster for precise landing before engine failure. Navigation, trajectory shaping, orientation, grid fin control, all performed above expectations. If the engine worked, this could have been one of history's most successful first attempt landings. That's why next attempt success is achievable. Landspace has flight data, detailed failure analysis, and proven guidance systems. The deeper question: what role does SpaceX play in their path forward? ZQ-3 uses stainless steel like Starship, liquid oxygen and methane like Starship, shape and grid fins resembling Falcon 9. These represent conscious design decisions based on SpaceX's proven approaches. Landspace will study how SpaceX manages methane flow, engine chill down, ignition sequencing, thrust vector control. They'll analyze Falcon 9's descent trajectories, landing burns, leg deployment. Comparing operational knowledge with flight data refines their approach. Critical distinction: copying appearances versus understanding engineering. Many startups imitate external features without grasping what makes systems work, struggling repeatedly. If Landspace focuses on actual engineering principles, failure modes, operational behaviors, design trade-offs, rather than replicating visible features, they have realistic success paths. SpaceX encourages this by being aerospace's most transparent company. Tests, launches, failures, successes broadcast real-time on social media. They don't hide progress, suggesting no worry about competitors catching up. Why? Because catching up requires SpaceX stops innovating. They show no slowing signs. As companies work toward landing first boosters, SpaceX already catches both stages with mechanical arms, deploys unprecedented payload scale, pursues full rapid reusability no one else achieved. This creates fascinating global industry dynamics. Every competitor improving by studying SpaceX validates their methods while confirming the gap between them. The race isn't catching SpaceX anymore. It's whether anyone maintains their innovation pace. With 5 Starship pads developing, 152 annual landings planned from single sites, V3 pushing toward January debut despite unprecedented technical challenges, that pace accelerates. Here's where we stand. SpaceX secured approval for 5 Starship pads with infrastructure supporting 152 annual landings from SLC-37 alone. Construction started. B-19 stacks at record speed toward January, Flight 12 with untested Raptor 3 engines and systems introducing unprecedented risks. China's Methane rocket proved landing boosters remains brutally difficult even when everything else works. This isn't just SpaceX moving fast, it's the entire aerospace industry being forced to evolve or become irrelevant. Landspace will learn and retry. Blue Origin will refine New Glenn. But the gap widens. While competitors work toward landing first boosters, SpaceX builds infrastructure to catch hundreds yearly across multiple sites. The real question isn't whether SpaceX can pull this off. They will. It's what happens when one company operates at unmatched scale. Which rocket are you betting on? Starship with 5 pads and mechanical arms? New Glenn with Blue Origin's resources? ZQ-3 and China's determination? Or Neutron and smaller innovators? Drop your answer in the comments. Think Flight 12 launches in January or V3's challenges push to February. If this breakdown gave you new perspective, hit that like button. Share this with anyone who thinks SpaceX is just another rocket company. Subscribe to New Space Review because the next few months define spaceflight's future, and you won't want to miss a single development. This is just the beginning.